Our topic for today is Lesson 7-4, Similarity in Right Triangles. Our learning goal for today is that today I will learn how to find and use relationships in right triangles. We're going to begin today's lesson with a review, and our review question is, what are the different parts of a right triangle? Remember that in a right triangle, we always have a right angle. And this right angle, remember, is always 90 degrees. Additionally, we also have special names for the sides of a right triangle. The side across from the 90-degree angle is always called the hypotenuse. The other two sides we have left over, so this side and this side, are called the legs. Now there's one more piece of information I want us to add to this triangle. So we're going to add in this line here. This line here is called the altitude. Now the altitude is basically just the height of the triangle, because remember that the altitude goes from one of the vertices straight down to the opposite side and meets at a 90-degree angle. So again, just to recap, we always have a 90-degree angle in a right triangle. The side opposite the 90 degrees is called the hypotenuse. The other two sides are called the legs. And then additionally, we added in this extra element, this line here, which is called the altitude. The next question we're going to explore is what is created when the altitude is drawn to the hypotenuse of any right triangle? This can be answered with Theorem 7-3. This theorem states that the altitude to the hypotenuse of a right triangle divides the triangle into two triangles that are similar to the original triangle and to each other. So basically what this theorem is saying is that if ABC is a right triangle with right angle ACB and with CD being the altitude to the hypotenuse, so again, if we have triangle ABC, again that's our right triangle, with our right angle being ACB, so this is our right angle, and CD is the altitude going from the point C to the hypotenuse, then we know that this triangle is divided into two triangles that are similar to the original. So we have this triangle ACD. So I've just flipped it around. Again, we've got ACD. And then we also have this triangle here. So the smaller triangle, the CDB. Again, I flipped this one around, so we've got CDB. Notice that D was our right angles, so we've got D here as the right angle and D here as the right angle. And then finally that original triangle, this ACB. So again, the altitude to the hypotenuse, so this altitude CD of a right triangle divides the triangle into two triangles that are similar to the original. So these two, the green triangle and the blue triangle, right here and here, are both similar to the original triangle ACB. So we could write our similarity statements here. So here we have triangle ABC, so ABC is similar to ACD, and we know that triangle ABC is similar to triangle CBD, and then also we can compare ACD and make it similar to CBD. So the main thing you need to know is that anytime we have a right triangle whose altitude is drawn to the hypotenuse, then it always creates two smaller triangles that are similar to the original. Our next question is, what is a geometric mean? For any two positive numbers a and b, the geometric mean of a and b is the positive number x such that a over x is equal to x over b. For example, if we were to try to find the geometric mean of 6 and 15, we would need a number that would satisfy this equation. So we would need it to be that 6 over some number x would be equal to x over 15. Now we can solve this simply by cross-multiplying. So I would take 6 times 15 and x times x, and then I would have to solve for x. So 15 times 6 would give me 90. And this needs to be equal to x times x, which is just x squared. Now to undo a power, we need to take the square root. So we'll take the square root of both sides. So we get the square root of 90 is equal to just plain old x. Now if I factor this, we know that 90 can be made with 9 times 10. And 9 is a perfect square, so that means we can take it out of the radical, so we would get 3 square root of 10 is equal to x. So the geometric mean, so the answer to this question, the geometric mean of 6 and 15 is 3 square root of 10. Our next question is, how is the length of the altitude to the hypotenuse of a right triangle related to the lengths of the segments of the hypotenuse? And this can be explained with corollary to Theorem 7-3. This corollary states that the length of the altitude to the hypotenuse of a right triangle is the geometric mean of the lengths of the segments of the hypotenuse. So all this is really saying is that the length of the altitude to the hypotenuse, so from here to here, we'll call that CD, the length of this altitude is the geometric mean of the lengths of the segments of the hypotenuse. So the segments of the hypotenuse is just AD and also DB. So the altitude is the geometric mean of AD and DB. So remember when we learned about geometric means, we knew that the geometric mean was the number x that satisfied this proportion for any positive number a and b. So as we said, CD is going to be the geometric mean of AD and DB. So CD will be our x value, so CD goes here and here, and we know that it's the geometric mean of AD and of DB. So for example, let's say the altitude of this triangle here is 4, and that its segments are 8 and 2, then we know that we could write the proportion 8 over 4 is equal to 4 over 2. So if we reduce this down, we know that 8 over 4 equals 2 and that 4 over 2 equals 2. So this does check out, that yes, 2 is equal to 2. So let's check. Our final question is, the legs of a right triangle is the geometric mean of the lengths of which two parts of a right triangle? This can be explained with the corollary 2 to Theorem 7-3. This corollary says that the altitude to the hypotenuse of a right triangle separates the hypotenuse so that the length of each leg of the triangle is the geometric mean of the lengths of the hypotenuse and the lengths of the segment of the hypotenuse adjacent to the leg. So if we have the right triangle ABC with the altitude CD, then AB over AC is equal to AC over AD. Because again, AC, which is one of the legs, is the geometric mean of the hypotenuse. Again, it says the geometric mean of the lengths of the hypotenuse. So our hypotenuse is here, the AB, and of the segment of the hypotenuse adjacent to the leg. So adjacent means next to. So it's also the geometric mean of AD, which is right here, which is the segment or part of the whole hypotenuse that is closest to the leg that we're talking about. Now the other proportion would be where we're talking about CB as the leg. So that would be AB, again the hypotenuse, so AB over the leg CB should be equal to CB, because again the leg is the geometric mean, over the segment of the hypotenuse closest to the leg that we're talking about, so over DB.